Okay, it's recording. So we're gonna start the second part of the class today. Just going back at what we have seen, we are gonna solve for this equation here. I hope you understand the meaning of this equation. So this is a sorry, I had a problem with my microphone, but I hope it's working now. So we are solving for this equation here. This term is a simplification of this here, just in order not to write all these terms here. We have transmissibility from any border of the block. So if it's a Cartesian block, we have 6 borders. But of course, we have a very irregular grid. We can have more than that, as we're going to see in some examples. So this is an important term that accounts for the mass that's going in and out of the borders. This is the mass that's going in and out of considering the wells. And this is the amount of mass that's accumulating in the block. Okay. So this is a general, as I have seen. It works for any simulation, composition, or black oil, or thermal. But now we are going to simplify the equations for the black oil, trying to show you how these equations are put into the simulator, and how they are solved, and which are the problems with solving this equation, and so on. And of course, we are going to do that for black oil because it's much simpler than the others. But it's the only thing that is more complex for compositional models is that we have to account for other aspects of the fluid behavior when we have compositional models, and we have more equations. Okay, but if you understand the black oil models, it's a very good start. Okay, that's why we are trying to explain you the black oil models. So again, we have 3 phases and 3 components in the black oil model. And that's how we always use CMP. We're going to have these options, so oil, and oil. So this is the amount of component oil that's inside the oil phase. This is the amount of component oil that's inside the gas phase. This is the amount of the gas component that's inside the oil phase. The amount of gas component that's inside the gas phase, the amount of gas component that's inside the water phase, and this is the amount of water that's inside the water, okay? The phase water, so component and phase. There are some special black oil models that have these red parts here, but generally, the ones we use don't have these parts. So this is an important simplification because the heavy components, which is the oil, it's only in the in one phase, just in the oil phase. The light components, it's in the oil phase and the gas phase, as you're going to see here. And the water component is only in the water phase. So this simplifies a lot our equations, not only because we have less components, but we don't have all the components in all the phases. So again, the water component is only in the water phase. The oil component is only in the oil phase because it's a heavy component and it's not going to turn into free gas in the reservoir. And only the gas component that sometimes is, depending on the pressure, it's inside the oil phase, and some, depending on the pressure, it's free gas in the reservoir. So that's the 4 terms that we have to account for, okay, in our equations. And of course, some of the premises we use is isothermal because we don't have temperature changes. We have instantaneous phase equilibrium, which is not always true, but for us, it's going to be true from this point on. And we have no chemical reactions as well. So if we have any chemical reaction that have to be accounted for in the reservoir, we have to add additional equations. But in our case, remember again, the fluid is moving only because of gravity, a difference in pressure, and capillary pressure, okay? Okay. Another thing that's a little bit confusing for you, but if you are petroleum engineers, you already know that. But if you are from other areas, we are we have some different nomenclature from other areas of engineering. So I'm going to give here a little bit of this nomenclature, but this is not very significant for us. It's very important for you if you're attending the reservoir engineering classes. Here I'm just giving you, of course, if you're going to write a reservoir simulation code, then it's important for you to understand this in details here, okay? But the problem is that petroleum engineers that write reservoir simulations, instead of writing mass balance equations, they write volume balance equations. And so we have to convert all the conditions to standard conditions. So don't bother if it's confusing for you, but I'm just giving this because all the books, all the papers, everything, when they write the reservoir simulation equations, they write component equations considering the volume, conservation of volume. But as we cannot solve it for pressure, for phases, because the phase is changing with pressure and temperature, we also, the volumes also change with difference in pressure and temperature. So the right thing to do would be to conserve mass and not volume. But of course, if I pick up the volume and convert to a standard condition, I can also conserve volume, okay? So this is a confusion that sometimes it's a little bit confusing in the petroleum nomenclature, but it's okay. I'm just changing all the volumes in place conditions, in situ conditions to standard conditions. Then I write the mass balance equations considering the volume mass balance equations, and then I go back, okay? Okay, taking to this nomenclature, the VP here is the volume of the phase. The VCP, again, is the volume of the component that's inside the phase. B is the formation volume factor, which is the ratio between the volume of phase P in the reservoir conditions, considering the standard conditions. So that's what I was talking about. So if I want to write the equation in terms of volume, I have to convert everything to standard conditions. So I use this factor here to convert the conditions from the volume, the reservoir conditions to standard conditions, okay? And R is the solubility of the components in the, I would add here, adds RCP, is the solubility of the component in the phase. So I have the solubility of the water in water, I have the solubility of oil in oil, and the solubility of gas in gas. They are all one. The solubility of water in oil is 0, remember, because we don't consider the water component in the oil phase. We don't consider the oil component in the water phase, and we don't consider the water component in the gas phase. So these are all 0. And the others are terms that we have to solve for, okay? So here I'm going to go very fast because it's not our intention to give you details in the equation. So once we're going to write these equations here in terms of black oil formulation, we have to convert everything using the variables that we have measured in the laboratories. So what we have in laboratories are the formation volume factor, the solubility, and so on. So we are converting this nomenclature in the black oil nomenclature here, okay? So it's not important, but we are writing here the solubility in terms of solubility of the component in the phase. Then we have to consider the density of the phases. Then we divide by the volumes. We convert this to the standard conditions. And then we calculated the YCP, which is the amount of the component that's inside the phase. And we're going to convert this using the solubility equations, okay? So when we finish this, we have this table here that if you need more details in how to get to this table, all the reservoir simulation books have, but instead of writing the equations using ICPs as we do here and here, here, we use this equation here. And so we write this in terms of solubility of the component in the phase, okay? And why we do that? Because for a compositional model, normally we have a thermodynamic model, a thermodynamic program that calculates the amount of the component that's inside the phase. But for the black oil model, we normally go to the laboratory and then we measure how much in each condition, each pressure, how much of we have of each component in each phase. And this measurement is done in terms of the solubility of the gas. So instead of writing this equation here, then we would have to convert all the ICPs into the variables that we know from the laboratories, okay? So we have this, which is the same equation as before, but written in terms of the conditions that we know in laboratory. Here is, again, the solubility of the component in the phase, and here is the formation volume factor of the phase to convert to the standard conditions. So this term here, again, is the same thing that we have seen before. It's amount of the phase that's going in and out of the solution. If we multiply the amount of the phase that's going in and out of the block, multiplied by its solubility, here we have the amount of the component that's going in and out of the block, okay? Here's the same thing for wells, but again, we have to convert for the solubility and for the formation volume factor. And here is the accumulated mass that we have in the block, but again, we have to convert it in the solubility and the formation value factor, okay? So this equation is the same thing that we have seen before, but written in terms of R and B, okay? And this is a common equation that you normally see also in the reservoir engineering class. Probably you are seeing this equation several times if you are taking PP301 or 302, okay? And again, the velocity here is given by Darcy's law, and the rest is the same as we have seen before, okay? In terms of well, of course, we want to express the well in the same way. So we have the rates of the phase that are producing from the well, and to know how much of the components, and we have first to convert to a standard condition divided by BP, and then multiply by R, which is the solubility of the component in the phase. So for example, if we produce 100 cubic meters of oil, we have amount of oil and gas dissolved in this phase oil. So we have to multiply by R CP from ROO and RGO, for example. So if you produce oil, we are producing not only oil, but also the component gas that is inside the oil, and so on, okay? So that's the only difference, because at the end, we want to know how much of the components is going in and out of the block. So this term is the same thing as the equation we have seen. So here's the difference in potential, as we have seen in the previous equation. And here is the transmissibility of this CP, okay? Here is the amount of mass that's accumulating in the block, again. And here is the amount of mass that's accumulating, is going in and out to the wells, okay? It's missing a well, W here. And this mobility here, if you remember from the transmissibility equation, is proportional to the permeability, to the relative permeability, to the viscosity, and also has to be divided by the formation value factor of the phase, okay? So this term here, RCP times mobility, is the same thing as we have seen here in the transmissibility here, okay? So here's the transmissibility multiplied by the difference in potential between the two blocks. So if you had two blocks and we have a difference in potential, they are gonna move from one block to another, according to the difference in potential we have from these two blocks, and according to the transmissibility among these two blocks, between these two blocks, okay? Here's the same thing. So the fluid is gonna move from one block to another, according to the difference in potential, according to the mobility of the phase, and to account for each component, we have to multiply by the amount of the component that's inside the phase, okay? And again, we have these three terms, which have all three together have to add 0 at the end, okay? And that's why we normally do this in terms of RCP and BP, because normally when we go to a lab, we take a little bit of the oil in the reservoir. We go into a lab, and I have a PVT table, which is like this, for example. And we go into the lab, and we change the pressure, and we measure the solubility. Here's the RS, which is the same as our GO in our case, which is the amount of gas that's inside the oil phase. Here, for example, is the formation volume factor of the oil. We measure the viscosities, for example, of oil and gas and water and so on. We measure also the compressibility, or we can measure BG, as the same here. And then we have BW and viscosity of water and so on. So normally we have a PVT table like this. So in terms, when we are going to write the reservoir simulations, we're going to input these tables inside the reservoir simulation. So every time we need the properties of the fluids, we go into these tables, and according to the property, for example, a pressure of the block, we have the formation volume factor, we have the viscosities, we have the solubility of the gas in the oil, and so on. So all the properties are measured in the laboratory, and we have this a typical table that we have inside the simulation code, and all the properties are measured in terms of pressure. Okay. Why only pressure? Because the temperature is constant, right? Otherwise, we would have to have pressure and temperature. Okay. So at the end, considering also that we have no oil in the gas phase, no gas in the water phase, and so on, as we have seen, we are going to end up with three equations. The first one is the conservation of water components. And then we have these three terms: the amount of water that's going in and out of the blocks, the amount of water that's going in and out the well, injector or producer, and this is the amount of water that is accumulating in the block. For the oil components, we also have these terms here. We have the amount of oil that's going in and out through the surface, in and out through the wells, and also the amount of oil that's accumulating in the block. And the only difference is in the gas component, because the gas component can be a free gas in the reservoir. So if we have a free gas, we're going to have a movement of the free gas phase, and then we have to multiply by this, and then account for the amount of gas that's inside the free gas, which in our case, the RGG is 1, okay? Because all in the gas component, in the gas phase, we have only gas component, but we also have the gas component in the oil phase. So we have to account for the amount of gas that's inside the oil phase, okay? So that's why we have the movement of the oil phase. Then we multiply that by the amount of gas that's inside the oil phase, dissolved gas, okay? So if we add these terms, we have the amount of gas that's going in and out the surface of the block, okay? The same thing happens for the accumulation term, because we have free gas and have gas dissolved in oil. And the same thing we have for the amount of gas that's being produced through the wells, because we can produce the free gas, or we can produce the oil phase, but inside the oil phase, there are some components of gas, okay? And the amount of components of gas that are measured are these RS that we measure in the table here. So for each condition, we have a different amount of gas that's inside the oil phase, okay? And these are the three main equations that we have for the black oils. And when we are solving the black oil simulation, we are solving these three equations every time step for every block. So we're going to have three equations per grid block per time step to solve, okay? Any questions? No? Okay. So, the first part, I try to explain you how the physical models are written in terms of mathematical equations. And in the second part, I try to show you which are the equations we are going to use for our simulation, which are these ones, okay? And these are general, can be for compositional model, for thermal model, and for black oil model. And after that, we using these equations, considering the black oil model, I try to show you how we convert that equation into our nomenclature from petroleum engineering and reservoir engineering courses, which at the end, we're gonna end up with these three equations. So every time we go to books and see black oil models, they start from these equations here to write the simulation equations. So I was just trying to show you that these equations can be developed by these simplifications that we use here. So we are applying the conservation of the three components we have in our system, water, oil, and gas. And they are moving through the surface of the block, which is these transmissibility terms here. They are accumulating in the blocks, which is these cumulative terms here. And then we have the wells here. So we have these three terms. And then we are, in the next part, we're going to show you how we combine these three terms in the equation and how we solve this inside a reservoir simulation model, okay? So let's go into our third part here of the class today. And again, feel free to ask me questions if you have any, okay? Okay, so in the third part, I'm trying to concentrate in the, I'm gonna, again, give you very, very superficial hints in how we solve the problems. I'm gonna try to show just a little bit of the numerical approximations we use for the equations. That's not to give you this subject too deep, because these are important when we are building a reservoir simulation code, but just superficial enough for you to understand that we have some errors, and these errors are proportional to the size of the grid block, proportional to the size of the time step, and so on. So then we're gonna use these concepts in order to try to pass you some details, how important are the selection of the grid and the time step and so on for our case, okay? Okay, this is just a normal finite difference approach, just to show you, for example, in our example, remember that we have a block that's called I, then we have two neighbors, a right neighbor here and a left neighbor here, and we have a distance here that's x, and x minus delta x here, and x minus plus delta x here. I'm gonna show the approximations we use. I talked a little bit about this last week, but we can use several approximations to write numerical equations here. We can have forward approximations, backward approximations, central approximations, and we can, for example, if we're writing the velocity of the phase in terms of the blocks, the velocity of the phase in xi plus 1 is the velocity of the phase I plus delta x, the variation of x in the x direction. Then we have other terms here. And what we do normally, we linearize this equation, simplifying these terms, assuming that these terms are very small. And if they are small, I can simplify the equations using this term here, assuming that the difference in velocities between the two blocks that we are going to use, for example, I can use this for potential, I can use this for velocity, and so on. So if you want to approximate any variable, in this case is u, or velocity, I can approximate using this approximation here, but I can use several types of approximations, and as I show here in the blocks. The most important thing that I want to emphasize here is that when we do this, we have a truncation error, and this truncation error is causing some numerical errors that we have to consider in our solutions, okay? Why? For example, let's assume that I have a very simple equation here. I have x here, and I have u here, okay? So I'm trying to, I'm trying to account, here is y, here is I plus 1, And what I do when I simplify the equations by using this thing here, I'm assuming that in this part, let's take another color here. I'm assuming that in this part here, I have a straight line that's given by this first part here, the block, okay? So this straight line here, I'm sorry, this second part here, is an approximation for the red line here, assuming that these two terms here are 0, okay? And of course, if this distance between I and I plus 1 is very small, this is a very good approximation. But if the distance between I and I plus 1 is very big, and this variation is very significant, then these terms can be high, and then I have a truncation error that is bigger. We normally say that this truncation error, we put all together in a category that we call numerical approximations, okay? So when I'm solving the equations using these finite element methods and approximate the solution, linearizing the equation and solving them in this way, we have these errors that we call numerical errors, that there are a lot of information about this in the books and in the papers. I'm gonna go very briefly here. The most important part here is just for you to consider that in our area, the size of the grid block is high, so these numerical errors are very significant, okay? Okay, if you want to solve equations like this, just a simplification of the equations, I'm gonna approximate, for example, this equation here by using this approximation here. So instead of using this, I'm approximation this using this simplification. This is a way we can solve an equation very simple like this one, for example. This is an equation simple for you that you vary considering the time and the distance, okay? So when we approximate this mathematical equation by this finite difference method we are solving for this, we are approximating this by this, but we have a numerical error here. And we are assuming that these numerical errors goes to 0. And when we have this approximation or this approximation here, this one or this one, and we put in this equation, we have numerical errors that have to be considered, okay? So we have errors that are proportional to the size of the grid block, and we have errors that are proportional to the size of the time step, okay? So this is just a message that if we have a smaller grid block, the errors are smaller, and we have smaller time steps, the time steps are also, the errors are also smaller. So, but of course, if you have more blocks, we have more equations to solve. We're gonna take us more time to solve. And if the time step is smaller, also we're gonna solve more times, and we have more time to solve the problem. So again, it's a compromise between what we can do in the time we can save, and this is very important for us. We're gonna see some practical applications. And probably you are seeing some of this when we are selecting your models for the project you are doing. So I'm not going into this, I just put this information for you to understand. If you have interested in the numerical part or aspects of this solution, there are a lot of things in the books, okay, but we are not concentrating our course in giving this information for you, because our focus here is not to write a simulation code, but to use, okay? But this is very important for us to understand that these numerical methods, they are solved in a numerical way, and sometimes they don't converge, sometimes they are not consistent, or they are not stable, and the cause for that is because of these errors and these approximations that we do, okay? So we are gonna see sometimes, even in your case, sometimes you're gonna see that simulations have problems in convergence. We're gonna talk about that when we finish explaining the numerical model, okay? What we can do to prevent this. But today, the commercial simulators have a lot of things inside them that prevent from these convergence problems. But the most common thing that they do is, if you have convergence problems, they decrease the size of the time step. So if decrease the size of time step, we are decreasing the errors, we are decreasing this this variance here. So we cut the time step in half and we solve again and so on. We are going to see some details about that probably next class or the other. Okay. I'm not talking about stability and conversions and these things, but this is very important if you are writing a reservoir simulation code. For us, it's not so important. Okay. Okay. Now, again, we are going back to the equations. We have the three terms we were talking about. The first one is the cumulative term, which is the variation in the mass from the time n+1 and the time n. So again, we are taking the volume of the block, multiplying by the porosity, which is the porous volume, multiplying by saturation. So we have the phase volume here. Then we convert this to a standard condition using the PP here. And then we account for the amount of the component that's inside the phase, multiplying by the solubility of the components in the phase. Okay. If we do this at the end of the time step minus the beginning of the time step, we have the variation in mass that we have in the block. Okay. The flow term that we call, so we are always calling this cumulative term. This is the flow term, which is the flow that we have from the neighbors. So again, we have the difference in potential. And here is the difference in potential. Is a third index of the phase P, okay? And here's the neighbor block, which is we call here N1, N2, N3, N4 for this example. And here's the block we are talking about. And here's the transmissibility of the phase and of the component in the phase, okay? So again, if you want to account for the amount of the component that's going in and out of the block, we have to account for the variations in the potential and the transmissibility, okay? And again, remember that the transmissibility was a geometric factor here, that's a function of the size of the block, is a function of the relative permeability, function of the viscosity, and function of the solubility of the component, okay? And here we account for pressure, for gravity, and for capillary pressure, right? So this term here, which is account for all the geometric part, is a function, of course, of the geometry of the blocks. So here I'm giving some simple examples how we write this geometric part in terms of a Cartesian block, which is very simple to the model, considering X and Y. For example, if you have X and Y here, we have, for the I block here, we have delta X and delta Y here. And considering here the same nomenclature we are using, for example, Y, I+1, I-1, I-half, and so on, we can write the geometric parts of the block by considering the area. So again, the transmissibility will be proportional to the area of the block, okay? And here we have a distance, and we divide in these two parts because the permeability of the blocks can be different. So in this part here, we account for the permeability, and we account for the distance between the two blocks, okay? We do this for the Y directions, we do that for our J direction, the K direction. So we have the geometric factor for the three directions that we are going to input here in this term here. So the transmissibility is then a function of the permeability, is a function of the geometry, is a function of the relative permeability, is inversely proportional to viscosity, and is a function of the solubility of the components in the phase, okay? So if you have a potential to move the phase from one block to another, we are going to calculate the amount of phase that's going in and out and multiply by this transmissibility. So we have the amount of components that's going in and out, okay? Here's another example for Cartesian and cylindrical coordinates. If you have, I'm gonna leave you here in the presentation just to let you know. In the literature, you can find this geometric factor for all the grid sizes, grid types you have, okay? And last, we have the well term, which is what we have seen already. We have the amount of, at the end, we have to have the amount of the components that's being produced. And this amount of components that is being produced is a summatory of the components that's inside each of the phases being produced. And the phases that are being produced are given by these terms here, which is the amount of the phase multiplied by the amount of the component that's inside the phase, and then we divide by the formation volume factor of the phase, okay? So just some particularities of the model here. So the primary variables we have in the implicit model are the pressure and saturations, and for the implicit models are the pressures, okay? I don't know if you remember a few slides ago, I show you that we have to account for all the pressures and also saturations. But as we know that saturation of oil plus saturation of water plus saturation of gas is equal to 1, I don't have to write the equations in terms of saturation of water. I'm going to write the equations only in terms of saturation, water, and gas, because the saturation of oil is 1 minus the others, okay? W minus Sg. And the same thing for pressure, because we have the oil pressure, we have the water pressure, and we have the gas pressure. That they can be different because of the capillarity pressure. But as we know the capillarity pressure, we can account for only one variable here, and the others will be calculated as a difference between the pressure of oil and the capillarity pressure, okay? So that's why we don't have 3 saturations and 3 pressures as equations. We have only 3 variables, which normally are oil pressure and saturation of water and saturation of gas. Of course, when the method is implicit, we are solving explicit for saturation, so our main variable is the oil pressure, okay? So our equations is this one, as we have seen. Now adding is this one, okay? As we have seen. And we account for these 3 terms, cumulative term, flow term, and well term, which are these 3 terms. And our main variables are these 3 variables. So we have 3 variables here and 3 equations. Remember, the 3 equations are the water equation, the oil equation, and the gas equations, as we've seen at the last slide of the second part of the presentation, okay? Okay, and how we are going to solve these equations? This is how we're going to show. So I have told you that if we add the flux terms plus the cumulative terms plus the well terms, the 3 add together have to be 0, okay? So the mass that's going in and out to the boundaries and the well can be the same mass that's accumulating into the block. But as we are solving this numerically, we are calling this RCB, which is the residual equations for the component C of the block B. And I know that these equations is valid only if the RCB goes through 0, okay? So as we are going to solve that numerically, we are going to give you an initial value, and then we are going to go through a iterative procedure where we're going to try to get the values of the main variables and try to check if the residuals are 0, okay? So let you explain you first a very simple equation, how we do this, and then I'm going to apply this concept to the mass balance equation in the reservoir. So assume that we have these equations, simple equations where f is a function of x, okay? And I'm going to solve this equation numerically. So let's assume that our equation is represented by this line here, okay? This blue line here. So how we are going to solve the numerical equations for the simulation blocks? For example, we're going to give you initial gas. In our case, will be an initial gas of oil pressure and saturation of water and gas, okay? In this case of this simple function, I'm gonna guess the x. Then I'm gonna go into this residual equation here, which is this equation here, okay? And I'm gonna check how much is the residual. For example, in this case, for this initial gas, my initial residual, R0, is this. So it's not zero. If it's not zero, my equation is not okay, because this residual should be a zero. If I get the right pressure and the right saturation of water and saturation of gas, the residual should go to zero. So this is the same for this equation. If I guess the right x, the residual should go to zero. So if it does not go to zero, how are we going to solve the equation? I'm going to calculate this derivative here. This derivative here is going to indicate the next iterative value for x. In this case, is x1. Okay. And then I'm going to check again the residual. This is residual 1. So I'm going to check if this residual is 0. If it's not 0, I'm going to do again. Let me just, I'm going to calculate the derivative again, and then I'm going to check the residual again and derivative again until I get to this point here, which is our solution, okay? So let's assume that I'm solving this f is a x, or x equals to 0. So this is the same equation that I'm solving here. So this is our function, and this is 0, and this is the residual, okay? So I'm writing the residual is a function of x is equal to 0. So if I'm going to solve this numerically, the way I'm going to solve is using this method called Newton-Raphson iterative procedure, where you're going to guess a value of our main variables. I'm going to check the residuals. If the residual is not 0, I'm going to calculate the derivatives, and the derivatives will send us to the closer to the solution, as we see here in the x1. Then if you calculate the residual again, we're going to see that the residual is still not 0. We're going to calculate the derivative again. And that's why the simulator keeps doing different iterative procedures, where we're going to try to, in the beginning, we're going to guess all the oil pressures and water saturations and gas saturations for all the grid blocks. We're going to check all the residuals. And for all the residuals, we're going to check if the residuals are 0. If they are not 0, we're going to use these Newton-Raphson equations. So this is the and we're going to get at the end of the process in the PO n+1, and the same for saturations, n+1 and n+1. So I'm going to go to the beginning of the time step to the end of the time step, try to converge to this solution here. When I converge to this solution, that means that I have this equation is okay. If this equation is okay, it means that all the mass balance equations of all the components for all the blocks are satisfied. So that means that for the end of the time step, I know all the pressures and saturations for my case, okay? I don't know if it's so okay, or if you have any questions about that, but this is the way we solve. I try to give you a very simple example here using a function that's very simple and just a function as a function of x only. In our case, I'm going to show now for different grid sizes how the equations will get. Instead of solving just one equation like this one, we are solving for 3 times NB, which is, if you have NB is the number of blocks, like 1 million cells. We're going to solve 3 million equations in this way. For each equation, I'm going to write the mass balance equations for that block. And I'm going to guess pressures and saturations for each block. I'm going to calculate the residuals, check if the equations are satisfied. If they are not satisfied, then we're going to calculate the derivatives that, in our case, are called Jacobian matrix, which is the derivatives of the equations, which are the same as here. So here I'm showing the derivative of x, for example. The derivative of x, how I calculate this x1. If I calculate the derivatives and I have the x0, I calculate the f of x0 and I have x0, I can calculate x1 here. Once I have x1, I calculate x2 and x3 until I go to 0, okay? Until I converge this process. So when I have just one function, I have this one. When I have a matrix, like I have in our case, the residual is a set of equations. For example, in this example here, I have 12 blocks. If I have 12 blocks, I have 12 equations, and then I will have 36 equations because we have to apply the mass balance equation for water, oil, and gas for every block, okay? So the xy here is our vector of the variables. In our case, it's pressure and saturation variables. Here are the residuals that have to go to 0. And here are the derivatives that we call Jacobian matrix, okay? So when we solve an iterative procedure in a reservoir simulation block, we are solving for this, okay? This is the most important concept we have inside the reservoir simulation blocks. So we are trying to solve this. And I'm gonna go the number of iterations that I need in order to converge all the pressures and all the saturations to the values at the end of the time step, okay? And this is the nomenclature we're gonna use from here, from this point on. The R are the residuals, the X are unknown variables, in our case are pressure and saturations, and J is our derivative matrix, which is called Jacobian matrix, okay? Any questions? Okay. So if you have 12 blocks, just as an example, let's assume that we have 12 blocks. We're gonna end up with a matrix that's like this one, where here we have the equations, and here we have the variables. So in our case, we have 12 variables here because we have 12 blocks and 12 equations here. And each element here is a 3 by 3 matrix because we have to account for oil equation, gas equation, and water equation. We have to account for oil pressure, for water saturation, and gas saturation, okay? So instead of 12 here, we have 36 variables, okay? Because each X here is a 3 by 3 matrix. But we have 5 diagonals here. Let's see if you understand the class. Why we have 5 diagonals here? Can you explain me why we have 5 diagonals in this matrix here? Anyone can answer this question? Are you there? Let's assume that this is the mass conservation equations for block 1, okay? I'm writing this line here as the equation for block 1. The question is, Jose is asking me to, why we have this, I'm representing here this term here. We're gonna solve for this system here, right? Where X here is a system that we have to solve. We have the residuals. We're gonna guess the pressure and saturations. We're gonna calculate the residuals. We're gonna calculate the derivatives. And we're gonna calculate the new axis, which is the new pressure and saturations. But when we have a grid block like this, I'm saying that we have these terms here. Why we have 5 diagonals here, or more simpler, why for block 1 we have terms here 1, 2, and 5, and here 0, here 0, 0, all the rest here is 0. Can you explain me how the rest is 0? Anyone can answer that? just putting one.
Good morning, Professor.
Mm-hmm.
I am going to try to attempt the question. I think the
Okay.
reason for the zeros are because of the missing assumptions in the black oil case. Like we don't have the gas in water phase, the oil in gas phase. We are only looking at the oil phase in oil, the oil component in oil phase, the gas component in gas phase, and the gas component in oil phase, and then the water phase only. I think, I don't know if that answers the question.
Okay, this is a pattern. We're gonna have some zeros in the equations because of what we are telling about. But this that we are telling about, we are gonna deal a little bit later. That are the terms inside here, because as I was telling, every X here is a matrix, right? For example, this first line here is the mass conservation block of mass conservation equations for components in block 1. So we're gonna have the mass conservation for oil, for water, and for gas, okay? And what we are telling is that some of these terms are zero, so we're gonna have some zeros inside these 3x3 elements here. But these are zero because of here, for example. Let's assume that we are writing the block 1 conservation equations. And the block 1 has two neighbors here, 5 and 2. That's why we have 5 here, because we have the variable, the pressure, for example, in block 2 is influencing the amount of mass that's going inside the block 1. That's why we have this second term here, okay? Because the pressure and the saturations in block 2 will influence the amount of mass. And as we have seen, we have this equation here, the amount of water and oil and gas that's going inside the block is proportional to the potential of the two blocks, the block N, as we have seen here, and the neighbor blocks, okay? So if the block 1 is neighbor of block 2, the variables in block 2 will influence the mass balance equations in block 1. That's why we have this second term here. The block 3 is not neighbor of block 1. That's why this is 0, okay? And the block 4 is also not neighbor of block 1. That's why this is also 0. But the block 5 is a neighbor of block 1. So that's why we have this term here, okay? So I don't know if it was clear, but that's why we have, in this case, as we have 2D model, we don't have the third dimension here. I'm only I and Y. We have each block has only 4 neighbors, at most 4 neighbors, okay? So we have the diagonal because, of course, the mass conservation equations of the block 1 will depend on the variables of block 1, but also they depend on the variables of the neighbor blocks, right? Why? Because we are writing these terms in terms of the flux terms is a function of the potential of the neighbor blocks, okay? So if the pressure and saturations are important for the flux from the neighbor blocks to the block, I'm have to consider when I solve the equations of block 1, if I change the pressure in block 2, this will change the amount of mass that's going inside block 1. So that's why we have to account for this effect, okay? And the same thing, if you see, happens for the other blocks. For example, let's assume block 6 here. Block 6 is a neighbor of block 2, is a function of block 5, it is a neighbor of block 7, and neighbor of block 10. That's why we have 5 terms here, okay? And the same thing happens to all the blocks, except the blocks, of course, that are in the borders here, because then block 1 do not have the left border here or the other part here. That's why the block 1 has only 2 neighbors, because he's in the corner. And block 5, for example, has only 3 blocks and neighbors, because there is no one of the blocks. Okay, but I'm showing this just to show you that if I construct a grid, this will influence the neighbors, and as I influence the number of neighbors I have, I'm going to influence the size of the matrix that I'm going to solve, okay? I hope it was clear, but what...
Professor,
Sim?
então a relação depende da configuração da grid?
Isso, depende da configuração do grid.
Tá.
Então, por isso que a escolha do grid é importante, né? That's why the selection of the grid is so important, because the size of the matrix that I'm going to solve is a function of the grid size that I'm going to put in the reservoir, okay? And of course, if I have a very complex grid with more than 5, 6, 7, 8 neighbors, I'm going to have a lot of terms there, okay? It's not only that. I was telling you last class that the Cartesian grid is not so bad as people say. Another thing that's very important is that when we solve this type of problem, we are not going deep into this because our class is more dedicated to use the reservoir simulations. But when we solve these equations, we have special mathematical methods to solve for different types of type of matrix. And when I know that a lot of this is a matrix that's a 36 by 36 matrix, okay, because we have these 36 variables and 36 equations. But if I know that there are a lot of zeros in advance, and if I know that the zeros are here and here and here, for example, all these parts, there is special ways to solve this matrix much faster, considering that I know that these matrices have 5 diagonals, okay? And this is one of the advantages of the Cartesian grid, because in the Cartesian grid, I know in advance that I'm going to have this simple matrix to solve. So not only we know that we have this number of neighbors, but also we know the type of matrix we're going to solve, so we can use simple methods to solve for this iterative procedure, okay? We are not going deeper into this, but just consider that when we are selecting the type of grids, okay? If, for example, we have a very complex grid, we're going to show a few examples later, I don't know, today or next class, but we have very complex grids, and each block has a different number of neighbors and very complex geometry. Then we don't know how this matrix is. We have to use different mathematical ways to solve the matrix. And normally, these different ways to solve are not so fast as we solve the pentadiagonal matrix, for example. Okay, just considering that. But we are not going to talk a little bit about that when we talk about the selection of the grids. Okay. Okay, for the black oil, then if you use implicit method, each residual is composed by the n residuals, where n is the number of blocks we have. So in this case, we have 12 blocks. So we have 12 residuals here. And each residue is a vector of 3 residuals, for a residual for the oil mass balance equation, a residual for water mass balance equations, and a residual for gas mass balance equation. So in our example, we have 36 residuals, okay? 36 residuals because we have 12 blocks times 3 variables, okay? And 3 equations to solve. And our vector of unknowns is given by x here, where every x is a vector of pressure and saturations. So in pressure and saturations, again, if we have 12 blocks and 3 variables, we are going to have 36 equations and 36 variables. And we are going to solve this system here, every iteration for 36 variables, okay? So how is the procedure? I'm going to guess 36 values, for example, 12 pressures, 12 water saturations, and 12 gas saturations. I'm going to check the residuals like we do here. If they are 0, okay, I'll go to the next step, time step. If they are different than 0, then I'm going to calculate this derivative. I'm going to calculate the new pressure and saturation. I'm going to calculate the residual again until I reach convergence. Okay, so when I reach convergence, I'm ready to go to the next time step. That means that the equations are satisfied for n plus 1. Okay, so now I'm going to show a more simpler than that. It's a case only for floor blocks, just to show you how is the equations in terms of terms. So again, we have here in this case 4 blocks, and we have 3 variables. So 4 blocks times 3 variables, we have 12 variables. Okay. So the block 1 is a neighbor of block 2 and 3. The block 2 is a neighbor of 2 and 4. The block 3 is a neighbor of 3 and 4. And the block 4 is a neighbor of 2 and 3. So these terms in white here are 0. The other terms can exist. And these x here are to account for these 3 variables and these 3 equations. Okay. And at the end, I'm going to solve this equation here. When I finish solving this equation, again, I'm gonna guessing the variables, pressure and saturations. I'm gonna use these equations to calculate the next iteration variables, and I'm gonna go into this procedure until I reach convergence. Okay. Of course, there's a question, does it mean that the simulation flow doesn't go into the diagonal direction? Yeah, it doesn't go into the, if you don't have an area, for example, if you don't have an area between blocks 1 and 4, remember that our transmissibility have a geometric factor here, okay, which is proportional to the area, which is this area here. Okay, so the geometric factor between the blocks, meaning that if you don't have an area between this block here and this block, or if you don't have an area between this block and this block here, we don't have a flux between block 1 and block 2 here. Okay, I'm using here what we call a normal 5-point scheme. So there are some special simulators that account for flux in the diagonal here, but we are not seeing details about this because they are not used anymore. In the past, we used to write equations considering these terms. There are some advantages and disadvantages of using this. I'm not talking too much about this as well, but in our formulation here, there is no flux between diagonal terms. So in this case, we have no flux between 1 and 4. That's why we don't have this term here and this term here. And we don't have flux between 2 and 3. That's why we don't have this term here and this term here. So when we write the mass balance equations for block 2, for example, the block 3 is not influencing on that. Only the blocks 4 and 1. And the same thing happens for the other blocks, okay? There are special ways to account for this diagonal behavior, but we are doing this. One way to do it is to write a different grid, for example. I can have a grid that is like this. It's not Cartesian, for example. Let's just assume I have a grid like this. So this will have this neighbor, and this neighbor. So now here I have an area, so I can account for that. So, but normally the geometric factor accounts for the area between the blocks. And if I don't have an area between the blocks, I have no flux between the blocks, because when I calculate the geometric factor, it's going to multiply by 0. Okay. If it's not clear, David, let me know. Okay. So again, we're going to solve this iterative procedure, and we're going to estimate x, calculating the Jacobian and the residuals. So first, we calculate the Jacobian and the residuals. We guess our variables. We calculate the Jacobian and the residuals. Then we calculate the new iterative x, and then we check for convergence in the residual and also in x. Let me see if I have a graph. No, I don't have here. And normally we account for both. Let's take here. Let's assume that I have these equations to solve. Remember that we are guessing this and trying to converge to this value here. So in order to check if we are converging, we put the tolerance here. And in order to converge, I select this tolerance here. for tolerance 1 and tolerance 2, for example. And only if all the residuals go inside the tolerance that I reach convergence. And also, because of the solutions can have a lower tolerance, but they are far from the X values, we also check for tolerance in the properties, okay? I don't know if what's clear in this example. Let's take this example here. Let's assume that my tolerance is this thing here. And then let's assume that this value here is inside the tolerance. It is okay for tolerance 2 here, but it's very far from the right value, which is here. So I'm checking normally in numerical methods if the tolerance of the residuals are going to 0, and also if the values of the variables are changing, not changing too much from iteration to another. That means that sometimes the tolerance is small, but I have a lot of solutions that are close to the solutions, as I saw here. All X's here are inside the tolerance range for the residuals, but they are very different in X. So sometimes I converge these two here. But anyway, any criteria that the simulator uses for convergence, when I reach this convergence criteria, I'm ready to go to the next time step. That's meaning that I reach the solution for n+1. And when I reach the solution for n+1, then I'm going to start everything again. I'm going to go to the next time step and converge again. So if, for example, n time is equals to 0, and my time step, for example, is 30 days. So initially, my n is 0, and my n+1 is 30 days. And then I go iteration by iteration until I converge to the right solution at the end of the time step. That means that in 30 days, my solution is satisfied, or all the equations here are satisfied, all the residuals are going to 0. That means that in 30 days, all the pressures and saturations are known at the end of the time step. So that means that I know what's the reservoir conditions at the end of the time step. And why we select pressure and saturations? Because if we know pressures and saturations, we can calculate all the other variables. All the geometric variables we know, if I know the pressure, I can go to the PVT table and calculate all the fluid pressures. I can calculate all the relative permeability and so on. So all the other functions are functions of these three main variables, pressure and saturations, okay? So at the end of the time step, if I know the pressure and saturations, all the other variables are known. So this will be the next time step. Then I go to n+2, and then I keep going until I advance in time. So in the beginning, for example, of the reservoir, all the fluids are in equilibrium. I'm gonna drill the wells. These wells will gonna cause the fluid movement. Then I have to understand how this fluid movement is happening in the reservoir. So I keep doing this mass balance equation for all the three components and keep doing this, okay? And the transmissibility here is calculated in function of the area, in function of permeability, function of the mobility of the phase, function of the geometry, okay? And I'm gonna give a little bit of details in this transmissibility because they are treated differently in the simulators, just to let you know, it's not so important, but it's good for you to know that the transmissibility, remember that the flux between the blocks are a function of the potential, right? So the potential is function of pressure, function of gravity and capillary pressure, okay? And also a function of the transmissibility here. And the transmissibility is a function of these terms here, which is a function of geometry, is a function of pressure, and a function of saturation. So once I know the pressure and saturations at the end of the time step, I can calculate all the transmissibility. And this transmissibility will be a function of these main variables, pressure and saturations, and function, of course, of the grid selection, which will give us a geometry, okay? And just to let you know, it's not so important for you, but it's important for those who are writing simulation code. The fractional pressure normally is given, for example, I need, let's pick up something that's a function of pressure. For example, the viscosity is a function of pressure. So I need to calculate the viscosity of the flux that is going from block 1 to 1 plus 1, for example. And in the block 1, I have pressure 1, and block 1, I plus 1, I have this other thing. So the viscosity in these two blocks can be calculated as an average viscosity between the two blocks, okay? Remember that if I have two blocks here, I and I plus 1, and I'm solving that numerically. So I have here viscosity 1, I, viscosity I plus 1, but I need the viscosity I plus half, right? Because it's this term that I'm writing here. Oops, I'm sorry. I need the viscosity of the phase I plus half. So I calculate as an average of this function. The same thing could be done for saturation, but for saturation we do a little bit difference that some people have shown. There are a lot of papers showing this and books that instead of taking the average for the saturation variables, we normally use these upstream conditions that we call, instead of using a midpoint weighting, we use an upstream weighting. I'm going to give you just a physical explanation why we do this in simulations. Let's assume that I have a block here, and let's assume that I have an injector here injecting water, and I have oil in the reservoir, okay? And the water is going to move, displacing oil in this direction, okay? So when I'm calculating the flux of this block that is displacing, for block 1, that's displacing oil into block 2, sometimes we have shown in the past mathematically that the solution is more precise if instead of picking up an average permeability, relative permeability, for example, of these two blocks, I use this upstream weighting, which is if the flux is going from block 1 to block 2, I use the properties of block 1. And if the flux is going from block 2 to block 1, then I use the properties of block 2. Why we do this? Because, for example, the flux of water that's going from 1 to 2 is not a function of how much water is in the block 2, but is a function of the amount of water that's in block 1 only. So that's why for the variables that are function of pressures, we use this midpoint weighting, which is an average between the two neighbor blocks. And all the functions that depend on saturation, we use this upstream weighting, which is a function of the block of the highest potential. Why the highest potential? Because the flux is always going from the highest potential to the lowest potential, right? So in this case of my example, is going from block 1 to block 2. So instead of taking the average properties from block 1 and 2, I take the properties of block 1, right? And it's shown in the literature mathematically and numerically that this solution is better and has less numerical dispersion, less numerical errors if you use this condition, okay? This is not so important for you that are gonna only use the simulators, but it's important if you one day you're gonna write the simulation code, because if you write these terms of saturations using the midpoint conditions for upstream, the solution is worse than the upstream weighting solution, okay? Okay, at the end, this is the type of solution we have. Let me take here. We are going in this iterative procedure. We are gonna solve for this equation again. And this equation accounts for flux, cumulative terms, and well terms. The residuals should all go to 0. And I'm going to go into this iterative procedure where I guess the main variable. Again, the main variables for the black oil model are pressure and saturations, as we have seen here. For the compositional models, we're going to see in a few classes from today that We also have to guess the components, how much of each component have, as you have to guess the phase. And we are going to keep doing this iterative procedure from the beginning of the simulation until the end of the simulation. Okay, and this is what inside the numerical equations of a reservoir simulation model. And next class, we're going to detail a little bit more of the consequences of solving these iterative procedures. We're going to see how the grid influences this iterative procedure, how we treat these three terms, in particular, especially the well term, which is very important, and so on. So I think for today, the important message that I was trying to pass is this. I try to show the equations that we solve, which is this one. We are counting for in the commercial simulators that the fluid is moving into the reservoir because of the pressure, gravity, and capillary pressure. These three terms are inside this potential here. If you are not familiar with these terms, you can read a little bit of reservoir engineering books just to understand how this potential is expressed in terms of pressure and saturation. For us, it's not so important here, but it's important for you to understand if you really want to understand what's inside the equation, okay? But then once we have this movement, do it through these three causes here, we're going to have a movement through the surface of the block. We're going to accumulate mass in the block, and we're going to have well taking and putting mass and taking out mass from the block. And we are going to solve in this iterative procedure anytime as we have n time steps. So what we're going to show you next class is the consequences of our choices in this type of model, okay? So for today was this. I don't know if it was too simple for you that already know the reservoir simulation things. Maybe it was too simple. Maybe for you that have never seen these equations before, it's a little bit complex because a lot of things I give very superficially. But I think the main points are this one for those who want to use the simulators. And next class, we are going to give you some other hints about this. Okay. So that's all for today. I'm going to stop the recording here, but I'm free to ask any questions, to answer any questions.